Okay, the final question, question number 6. The Maclaurin series for function f is given by this series and converges to fx for all x in the interval of a convergence. And it can be shown that the Maclaurin series for f has a radius of convergence of 6. Okay, question A. Determine whether the Maclaurin series f converges or diverges at x equals 6 and give a reason for answer. So, the Maclaurin series we were given has a radius of convergence of 6. So the center of this series, C, if we stretch on both sides 6, so this point is C plus 6, and this point is C minus 6. What this says is this function f, which is this series, has a radius of convergence of 6. Then, for all values within these boundaries, the series converges. But we're not sure at these two endpoints whether these two endpoints converges or diverges. So here, question number A is asking us if at this endpoint, at x equals 6, give a reason for answer. So at x equals 6, is it converge or diverge? Okay, so let's see. X equals infinity n plus 1 n plus 1 x to the nth power n squared 6n. So this is the series, and we just need to substitute x equals 6 into the x value. So okay, n plus 1 6 to the nth power. We can simplify this into n equals 1 to infinity n plus 1 n squared over n squared. Okay, so this is the series at x equals 6. Now we have to find out whether this series converges or diverges. So to find whether this series converges or diverges, let's use a test. So first, observe this n plus 1 over n squared. Now we can use the direct comparison test, because n plus 1 over n squared, if we tend n, so we let n approaches a very large number, then n plus 1 over n squared is similar to n over n squared, because 1 is insignificant here as n approaches a very large number. So n over n squared can be rewritten as just 1 over n. Now we know that this series 1 over n is a harmonic series, and a harmonic series should diverge. So we have to find if this n plus 1 over n squared is greater or smaller than 1 over n. Now let's plug several values here. So suppose n equals 1. 1 plus 1 over 1 is greater than 1 over 2. 1 over 1, okay? Now if it becomes n equals 2. 2 plus 1 over 2 squared is greater than 1 over 2. So n plus 1 over n squared seems to be larger than 1 over n. Now if n plus 1 over n squared is large over n, then the series of n plus 1 over n squared should diverge, because series of 1 over n also diverge. Okay, question B. It can be shown that f negative 3 is this series. So we just basically plug x equals negative 3 into the original series, which can be found to be this series. And the first 3 terms of this series sum to this value. Now we have to show that f negative 3 minus s3 is smaller than 1 over 50. So these kind of problems are error problems, and we're dealing with an alternating series. Okay, an alternating series. So an alternating series error bound states that f negative 3 minus s3, so this is the original value, the true value, and s3 is the approximated value. Now it states that it is smaller than 1 over 50, so we have to prove that it is smaller than 1 over 50. So the alternating series error bound states that the original value at this negative 3 minus the value, the third term approximated value, is smaller or equals to the next unused term. So which is the next unused term? So it is at n equals 4. Now where is n equals 4? Next unused term. Okay, at n equals 4. Let's see. N plus 1, so it's 4. Let's see. Then 4 plus 4 squared, 1 over 2 to the 4th power. This value can be found as negative 1 over 25. Okay, over 144. Okay, oh wait, and this is plus 4. Wait a minute. Okay. So 4 plus 1 over 4 squared, negative 1 over 2 to the 4th power. This is equals to, let's do that again, 5 over 16 times 16. This is equals to 5 over 256. This is smaller than 1 over 50. So we have proved that the error of the third term approximation is smaller than 1 over 50. Question C. Find the general term of the Maclaurin series for f prime. So this series is a Maclaurin series for the function f. Now we're being asked to find the function for the series for f prime, the derivative of f. Find the radius of convergence of the Maclaurin series of f prime. So let's write it out. N plus 1, n plus 1, x to the n power, n squared 6n. So this is equals to 1 plus 1 x. Okay, now we simplify this a little bit. Okay, 1 plus 1 n, okay, 1 squared 6, 1. Now if we differentiate this series, so f this is equals to fx. Now f prime x equals to this. if we differentiate this series, we would get 1 plus 1 x 1 over 2. We still have this 2, 2, 2, 6, 1 squared 6 plus 2 plus 1. 2 plus 1, 2x, 2 squared 6 squared dot dot dot. Okay, now let's rewrite this into a we need to find the general term, so let's rewrite this series. Now 2 1 squared 6, so this is the first term, this is the second term, so let's find a pattern. So we can write the missing x as x to the 0's power. Now we would get, so 1 plus 1, 2 can be written as 1 plus 1. So n plus 1, n plus 1. So 1 plus 1, 2 plus 1 is changing. N plus 1 to x. N minus 1. We also have this 2 and this missing 1 here, so we can write n. Then 1 squared and 2 squared, it is changing n1, n2, so it is n to the squared. And 6, this is 1 and this changes to 2, so it's 6 to the nth power. Okay, so this is the general term. The general term of f prime is this one. And find the radius of convergence of the Maclaurin series of f prime. So we were given that the f's radius convergence is 6. F's radius convergence. F's radius convergence for Maclaurin series is 6. Then f prime x radius of convergence is also 6. The radius of convergence for the fx f prime x, or the integral of fx, is all 6. Convergence is also 6, and it can also be proven using the ratio test. Question D, and the final question is, let gx be this series. Use the ratio test to determine the radius of convergence of the Maclaurin series for G. Okay, so we have to use the ratio test. So first, let's write that down. Limit as n approaches infinity. Absolute value. So we have to find the absolute value of the ratios of the n plus 1 term over the nth term. So n plus 1, let's make sure to write that n plus 1 down. Plus 1 to avoid mistakes. X and 2n plus 1. So this part is tricky too. N plus 1. You can't write 2n plus 1. So it's 2 parentheses n plus 1. N plus 1 squared times 3n plus 1 over the original series n plus 1 x 2n n squared 3n and absolute value. Okay, now let's rearrange this quotient here to a simpler method. Okay, x 2n plus 1, 2n plus 2 becomes 2n plus 2, n plus 1 squared times 3n plus 1. Okay, we times the reciprocal, n squared 3n over n plus 1 x to the 2n power. Great, now let's find ways to simplify this. N plus 2, n plus 1 we can. Leave that out. x2n plus x2n can be written as x2n times x squared over 3n times 3. Basic exponent properties here. And finally times n squared times 3 to the nth power over x2n. Okay. And the absolute value. Oh, there's squared, so this becomes to the 3rd power. Okay. Now let's rewrite this. We can write n plus 2, n plus 1 squared. x2n can and x2n can cross out. 3n can cross out, and we're left with n squared over 3 and x squared. Now we're dealing with a limit that is approaching n to infinity, so x doesn't really matter. So let's bring x out of this absolute value. Let's bring x out of this limit. So x squared absolute value, n plus 2 over n plus 1 cubed times n squared over 3. So let's deal with this limit first. N plus 2 times parentheses times n squared over n plus 1 cubed times 3. Okay. So n is approaching infinity, so n gets very large. 2n1 is insignificant. Okay, so we can view this as n times n squared over n cubed times 3. Because this 3 is times, it cannot be omitted. So we get basically n cubed over n cubed times 1 over 3. Now, limit properties makes this n cubed over n cubed to 1. Now, a limit of a constant is that constant, so this entire limit becomes 1 over 3 times x squared absolute value. Now, x squared absolute value is always positive. X squared is always positive, so the absolute value is not necessary. So we get 1 over 3 times x squared. Now, the ratio test says that this final value is smaller than 1. So now we have to find an interval for x. So this becomes x squared is smaller than 3. Okay, now we have to omit this squared. So we can say this absolute value, x's absolute value equals to the square root of 3. So we just put a square root on that. X squared square root is equals to the x's absolute value. So we have made it into this format. X absolute value is smaller than 3 square root, so the radius of convergence for G, the series is 3 square root. Okay, so this is all of the 2024 Calculus BC free response questions.